Hi everyone, welcome to the Earth Science Regents Review podcast series created by Homix Middle School Earth Science Department. Today we're going to talk about page 10 in the reference table, the inferred properties of the Earth's interior. Now the reason why it's called the inferred properties chart is very simply because we haven't dug a hole any deeper than 7.5 miles into the Earth. So the majority of our information comes through the study of earthquake waves and meteorite studies. So let's start off with the different layers first. The outer portion of the Earth is what we call the crust, and that's going to be indicated by the black outer line. Below that is a white line labeled the rigid mantle. Together, they make up what's called the lithosphere. Below that, you have the silly putty-like asthenosphere, and that's why it's called the plastic mantle, very simply because of its fluid-like properties. Because the heat is a little bit greater inside the Earth than at the surface at this depth, okay, that layer is going to be influenced by the temperature differences, which is ultimately going to affect the density. Now, density differences within a layer is what we call convection. Now, there are two convection cells. You have one portrayed on the west coast of the United States, where the Juan de Fuca plate is converging with the North American plate, producing the Cascade Mountains. And we also have one in the middle of the Atlantic Ocean, producing the Mid-Atlantic Ridge. This is a divergent plate boundary. Okay? Below that, you have the stiffer mantle. Below that, you have the outer core, made up of liquid iron and nickel. Below that, you have the inner core, made up of solid iron and nickel. Now, you notice that each layer has its own individual pattern. So that represents where one layer ends, the other one is going to begin. So the very outer portion of our Earth is the lithosphere. Where the lithosphere ends, the asthenosphere begins. As we travel deeper, where the asthenosphere ends, the stiffer mantle begins. We travel deeper. The stiffer mantle ends, the outer core begins. Where the outer core begins, the inner core begins, and we can go as deep as the actual center of our planet. Now, each layer actually has its own distinctive density range. So you'll see that the lithosphere, specifically the crustal part of the lithosphere, goes between 2.7 and 3.0 grams per cubic centimeter based upon what type of crust you're dealing with. You notice that there's a little boundary between the crust and the rigid mantle that's called the moho, which indicates that there's a stark density difference between those two layers. Earthquake waves not only change direction, but they also change speed as well. They speed up as they exit the crust and enter the rigid mantle. The asthenosphere, which is technically on the upper portion of the stiffer mantle, they're going to have a range between 3.4 to 5.6 grams per cubic centimeter. The outer core is 9.9 to 12.2 grams per cubic centimeter, and the inner core is 12.8 to 13.1 grams per cubic centimeter. Now that's the upper portion. Let's move to the middle section, and this is basically going to represent the pressure. Now you notice this section looks like a direct relationship if we were going to graph it out. Okay, the dark reference line is an upward sloping line, just like a direct relationship is. And that's the relationship between pressure and depth. As you go deeper into the planet, the higher the pressure. Just like with density, the deeper that you go in the planet, the higher the density. Okay? In this case, what you're going to do is you're going to extend your boundaries or your interfaces down until they intersect your black reference line. So we're going to take the lithosphere, the top of the lithosphere, bring it straight down. Okay? You can see that your pressure is 0, but you notice your units here, it's millions of atmospheres. Basically what this does is it measures what the pressure is like, how many millions of times greater it is inside the Earth as it is here at sea level. So on the lithosphere, we're at sea level essentially, your pressure is going to be 0 millions of atmospheres. Extend the bottom of the lithosphere down, okay, you're going to have a pressure of about 0.1 millions of atmospheres. So there is your lithosphere. Where the lithosphere ends, the asthenosphere begins. The asthenosphere will begin at 0.1 millions of atmospheres and extend down to about 0.2 millions of atmospheres. So there's your asthenosphere. Where the asthenosphere ends, the stiffer mantle begins. 0.2 millions of atmospheres to about 1.5 millions of atmospheres. So there's your stiffer mantle. Where the stiffer mantle ends, the outer core begins. 1.5 millions of atmospheres, okay, to about 3.1 millions of atmospheres. There's your outer core. And then where the outer core ends, the inner core begins. Okay, inner cores can begin at 3.1 millions of atmospheres, and the center of our planet is roughly 3.6 millions of atmospheres. Again, that's going to be the inner core there. That is the arc pressure. As you go deeper in the planet, the pressure increases. Now you're going to do the exact same thing with your temperature. You're going to extend the interfaces straight down until they intersect your black reference line with temperature. Again, direct relationship. Deeper you go on the planet, the hotter it gets. You notice that your temperature is in degrees Celsius. So the lithosphere, at the top of the lithosphere, is going to be about 0 degrees Celsius. The bottom of the lithosphere is going to be about 1,000 degrees Celsius. There's your lithosphere. Where the lithosphere ends, the asthenosphere begins. So the asthenosphere is going to begin at about 1,000 and it's going to extend to about 2,600 degrees Celsius. There's your asthenosphere. Well, where your asthenosphere ends, the stiffer mantle begins, 2,600 degrees Celsius to about 5,000 degrees Celsius. There's your stiffer mantle. Where the stiffer mantle ends, the outer core begins, 5,000 degrees Celsius to about 6,200 degrees Celsius for the outer core. Where the outer core begins, the inner core, where the outer core ends, the inner core is going to begin. 6,200 degrees Celsius to approximately 6,600 degrees Celsius at the center. Again, that's going to be approximately our inner core. So again, you notice it's a direct relationship between depth and temperature. Now you do see a couple dotted lines that are labeled melting points. Anytime the melting point is below the interior temperature, you're going to have a liquid layer. Okay, the interior temperature, when it's above the melting point, means the melting point has already been reached. That's going to be a liquid layer. You notice what layers they are? The asthenosphere and the outer core. So if the melting point's below the interior temperature, you have a liquid or semi-liquid layer. The last section we're going to deal with is depth. Okay, and again, you're going to bring the boundary points directly down to where they're going to intersect your depth range. So the lithosphere begins obviously at sea level and extends to a depth of about 100 kilometers. There's your lithosphere. Okay, your asthenosphere is going to begin at about 100 kilometers and extend to about 800 kilometers. There's your asthenosphere. Your stiffer mantle will begin at about 800 kilometers and extend to about 2,900 kilometers. There's your stiffer mantle. The outer core will begin at about 2,900 kilometers and extend to about 5,100 kilometers. There's your outer core. And finally, your inner core is going to begin at about 5,100 kilometers and extend to about 6,300 kilometers. Okay? So that's essentially the inferred properties chart. A lot of information here. Make sure you know how to read it. Thanks so much. We'll talk to you soon.